Alrighty, and we are live. Let's close that down. There we go. Welcome to Chem 420 online office hours. We are live. By we, I mean me. I am live. We have or I should get better with my pronouns. You have an exam this week, a lecture exam written by Max. I have not seen it, so I do not have the inside scoop as to what is on the exam. That being said, I do have the inside scoop on problem solving and figuring that whole situation out. So if you have questions, I am more than happy to answer them. I did receive one email that did have some homework questions or inquiries about homework questions, but unfortunately, I didn't receive pictures of the actual problem. So I don't actually know what's going on in the problem. I only see the included question. That being said, there were a couple kind of conceptual questions that we can hit and kind of go over some of the answers to some of the conceptual questions, and then if more people join or more questions trickle in, we can get those as they come. So first off, I guess you guys have been learning a little bit about Sn2, Sn1, E2, and E1. And the first question, kind of conceptual question that I received and we can talk about is this question. Can can H2O make hydroxide a good leaving group? All right, can water make hydroxide a good leaving group? And when you want to think about how to answer this question, so we want to think about the context that this question comes from, mainly the context of Sn1, Sn2, E1, and E2, all of those leaving group mechanisms. And we know that when we're I don't want this in yellow. We know that when we're dealing with hydroxide, I'm sorry. I just called an alcohol hydroxide. My brain is coming from Gen Chem land. I did Gen Chem lecture this morning, and I've been writing a problem bank to give an online Canvas exam for my Chem 400 class. So I apologize for calling an alcohol hydroxide. So we know that that OH is a poor leaving group. But by contrast, we know that water, a protonated alcohol, this right here is an excellent leaving group. So this is an excellent leaving group. And we know that we can turn OH into a good leaving group, right, through protonation. So the question that you have to ask is this: how do you take your OH, oops, what reaction do you need to do to turn your OH into a water molecule, at H2, to add that H and then add the positive charge? And the answer is the way you turn your poor leaving group into an excellent leaving group is through protonation. And you need an acid, you need a proton source that is stronger than the acidity of an alcohol. All right. Now, alcohol acidities are around their pKa range is around 16, 17. And when you look at the pKa of water, all right, so the pKa of H2O, water has a pKa of, I believe it's 15.7. And so when you compare the pKa of water to the pKa of your average alcohol, it's not significantly more acidic. It's we would say that H2O is slightly more acidic. Slightly more acidic. But not significantly more, so we would say, but not strong enough. When you want to turn your OH into a good leaving group, you want to use a strong acid. You want to use HCl, or sulfuric acid is another great one. You want a really, really powerful acid to protonate that alcohol so that it becomes a good leaving group, and you can, get on with the rest of your mechanism, whether it's Sn1 or E1. And reality is it's probably going to be a bit of both for that situation. All right, so that's the first conceptual question. Also, again, anybody who's watching live, totally feel free to jump in with questions at any time. I only at this moment have received one email, so I'm going to be kind of moving through that. Moving through that email until a better question arises. So oh wait, hang on. There we go. Wait, come back. There we are. So if you have a question, totally jump in. Lob it at me in the chat, or you can send it over. I've got both my Canvas message inbox and my normal email inbox open. So as I see questions coming in, I can totally address those. All right. So that is the answer to can water make OH a good leaving group? And it's really not acidic enough to be an effective proton source to turn hydroxide into a good leaving group. All right. Next question. Let's see. All right. let's see. This question's a little long. Hang on. Okay, so this is a general question. So this question, I believe, is asking, and totally feel free to correct me, asker of the question, if I'm not understanding your intention, but this question looks like the question is, if you have iodide, for example, which is a good nucleophile and a good base, is Sn2 prioritized over E2? And the same question for, is Sn1 prioritized over E1? How do you tell what is going to happen? This is a very, very kind of sprawling question, which is how to differentiate. How do you determine Sn2 versus E2, and Sn1 versus E1? All right. How can you figure out which mechanism is going to happen? And these tend to be the types of problems that are one of the hardest ones, to be frank, to answer. One of the hardest ones to answer when you are when you're first starting out on the second exam. It's traditionally, historically, one of the harder types of problems to address. Oh, hey, we got our first question in the comments. Can I do some synthesis problems? I totally can. Quick question. Yeah, we can totally do some synthesis problems. Oh wait, I should say also, do you have any specific problems? Or you like me? Okay. So we'll get to some synthesis problems after this question, and I'm going to this could be several hours of lecture in and of themselves, answering this question: how do you determine Sn2 versus E2 and Sn1 versus E1? So I'm going to give kind of a succinct summary, some specific things to look for, and then if you guys have, if something doesn't make sense, please give a shout out. Let me know. I can expound on it further. And also, if you have specific questions, or not questions, but problems that you were working, that you're like, okay, here's a problem where it's Sn1 versus E1, and I don't understand which one to go with. We can dig more into that later. But I'm gonna keep this answer as broad as I can. We are gonna get into the nitty gritty a bit. But then we can get more specific as this discussion generates more questions. Okay, let's see. Okay, we got another question. Reason why I asked a question is one of the homeworks stated it would be predominantly E2 as opposed to Sn2. Could also be done. Used. Okay. Totally. All right. So basically, first, if we want to, let's take Sn2 versus E2. Some things to look for. So some things to look for. The thing to remember about Sn2 is we're dealing with a direct displacement. So we have a strong nucleophile rolling in on a good leaving group, and that nucleophile does backside attack, displacing the leaving group, producing our substituted product and a new counterion. So that is Sn2. Now with E2, oops. E2 is also a bimolecular reaction. It's concerted. It happens all in one step. The difference is in an E2 elimination, instead of a nucleophile doing a displacement, you have a strong base rolling in, deprotonating a beta hydrogen, giving us an elimination product plus a conjugate acid plus our leaving group and ion. All right. So when it comes to determining which is which, it's important to remember some very specific requirements, because Sn2 and E2 each have their own kind of hangups, their own deal breakers. All right. So the first, and this is in no particular order, but one deal breaker, for example, for E2 is you have to have, so if the leaving group is attached to the alpha carbon, that means that the hydrogen we're eliminating is beta. An E2 mechanism must have a beta hydrogen. If it does not, then there's no dice. So if you have a scenario where you have a very good leaving group, a very strong nucleophile / base, and you're not sure which way to go, check to see if there's beta hydrogens. If there's not, you know E2 isn't an option. Another thing to look for with Sn2 has its own deal breakers generated by the whole backside attack mechanism that Sn2, or I should say backside attack transition state that Sn2 proceeds through. Because the nucleophile has to attack the leaving group from the opposite side, from the back, the leaving group cannot be sterically hindered. The leaving group must be on a primary or secondary carbon. All right. If there's a lot of steric bulk on the leaving group, the carbon with the leaving group, then it's not going to be able. The nucleophile won't be able to get in there and attack, and so as a result, due to the steric bulk of potentially the carbon, it's not going to be able, if you have if sterically hindered carbon or a very large nucleophile, sterically it's not going to be able to do a displacement, so it would favor elimination. All right, okay, beautiful. So I just got so this is kind of general things I look for. I look for the deal breakers in my substrates, in my nucleophile / base, to try to differentiate between what's going down. And Irving just sent me a picture of the actual problem. So let's use these kind of concepts, searching for those deal breakers, to make a determination one way or another. So in this problem, which this is problem 7. Oops. Let me open a new slide. This is problem 7.64 in your textbook. All right. And the question asks us to predict the major product. Whoa. There we go. Okay. So predict the major products. All right. And then they give us two situations. They give us example A, and they give us example B. Both A and B have the same substrate, but then as you see, they'll change up the reaction conditions on us. So here we have a secondary bromide, sodium hydroxide. All right, and here we have, again, same substrate, secondary bromide, and we have potassium terbutoxide. All right, so the first thing that I do when I'm being asked to predict a major product, obviously we're trying to determine what mechanism we're going by, because the mechanism of the reaction will determine what products are formed. All right, the first thing that I look at is the leaving group. And on both of these, because it's the same subject, we've got a good leaving group, right? We have a good leaving group, all right? The second thing, for both of them, the second thing that I notice is that the strong leaving group is on a secondary carbon, all right? So secondary carbon, totally possible to do Sn2 on a secondary. Primary is preferable, but secondary is still possible. Secondary versus primary doesn't really make much of a difference for elimination. For elimination, we need to see, do we have beta hydrogens? And the answer is yes, we do have beta hydrogens. Right, we have, I was about to say we have beta hydrogens on both of these substrates, but it's the same substrate. All right, so Sn2 is on the table, E2 is on the table at this point in time. We have strong leaving groups, we have beta hydrogens, we have secondary leaving group as well. Okay, so how do we pick which is which? We've so far focused all of our analysis on the substrate. Let's look at our reaction conditions. We know that sodium is a cation, right? So this has a positive charge, which means our oxygen is negatively charged. Same with potassium. Potassium's a cation, so that means our oxygen is anionic. For both of these, strong nucleophiles / bases are in play. All right, now let's look at the actual base. For part A, you'll notice our base is hydroxide, which is small. All right, if something is small, sterically speaking, that is good for Sn2. Because again, Sn2 has to do a backside attack. So it's going to be able to, because it is a small little molecule, hydroxide is going to be able to come in from the back, push the leaving group out, and do a nucleophilic substitution. Now, when you look at tert butoxide is huge. All right, this thing is gigantic. If you actually draw the molecule out, it looks like this, and not even drawing all the CH bonds. Tert butoxide is so large, it gets a nickname. This is called the E2 base. The oxygen, the anionic oxygen, is strong enough to do an Sn2, but the carbon chain it's attached to is too sterically large to be able to successfully do a backside attack on a leaving group. It doesn't matter what it's attached to. So potassium tert butoxide will only ever do an E2 elimination. All right. So I would predict for the first one, because it's strong and small, it's going to sneak in there, do an Sn2, and so we should get an inversion of configuration. And our product should be an OH. And for part B, the product here will be it'll be an E2 product. Now you may be going, hang on, wait a minute. Why didn't you draw the product? Why'd you just write an E2 product? And this is not me dodging work. Sometimes professors will be like, oh yeah, and you know the answer, just go figure it out. And it's really because we don't want to have to do it. I totally do, but I also am out of room on this slide. So to show you the products we're going to form, I just want a little more room to explain. So I'm going to pop to the next slide right now. All right, so let's take a look. So we've got, again, just rewriting, or I should say redrawing, our substrate reaction conditions. Now, potassium tert butoxide, as we said, is huge. And so it is going to prefer, the major product is going to come from the side that's less sterically hindered. All right. When you look at the beta hydrogens, so we have got two beta positions right here and here. This beta position is secondary. This beta position is primary, and because primary is less sterically hindered, the potassium tert butoxide, the major product for the elimination with potassium tert butoxide, will come from the less hindered side. So the product here, I guess I could have fit that on the other page. I thought it was going to be worse than it is, but turns out it's not too shabby. This would be the major elimination product, one in which potassium tert butoxide grabbed one of the three H's on that terminal methyl and eliminated it with the bromide. So this is the major product for that E2 reaction. Hopefully that that makes sense. Okay, so let's see if there are any questions that roll in with that. I'm totally down to answer. But we have one on the stack from Nilab asking for a synthesis problem. So let me scare one up here. Let's see what we got here. Doo-doo-doo. Okay. I'm looking for an interesting one. Okay. Here, how about this? Let's see. For A, couldn't we? Oh, okay. Sorry. Before we leave this, sorry, Irving, I just saw your question. So for A, okay, wait, that's on the previous slide. Give me one sec. So for part A, couldn't we get a Zaitsev? Oh, so you're saying could an elimination happen and we get a Zaitsev product? That is totally possible. That is totally possible. And probably would be a minor product. But due to the size, the nucleophiles, small size, I would predict a major Sn2 product. Yeah, so Irving, you totally could get a Zaitsev product for part A. But again, because the nucleophile is small, when you look, so if you're wondering, okay, again, we could get a Zaitsev, but when you're looking to kind of explain the nucleophile's behavior, when you look at the substrate, bromide is going to have a partial negative, and the carbon bearing the bromide will have a partial positive. So when you want to ask yourself which atom in this molecule is hydroxide most attracted to, the biggest attraction here is going to be between the negative charge on hydroxide and the partial positive on that carbon. So that is why hydroxide prefers to attack through Sn2. If it's sterically too bulky to get in there, then the base / nucleophile will look to surrounding hydrogens to do an elimination, but because hydroxide is so small, it's able to approach that partial positive charge on the carbon, and it'll lead to an Sn2 major product. All right. I found a synthesis problem that's decently good. We can maybe start here. I can totally, by the way, if this one example doesn't scratch the itch, we can do maybe a few more, because fortunately for us, the internet is the internet is filled with these. So I can keep finding. Oh, excuse me, sorry. Just bumped into my microphone. I can keep finding these off the fly and maybe even cook up some of my own. But here, consider the following synthesis problem. So starting from acetylene, which is this alkyne, how would you prepare the following molecule? Hang on. I'm going to draw this a little better. There we go. All right, so let's synthesize this molecule. Now, I cannot emphasize enough, whenever you're doing a synthesis problem, it's very, in general, not always, but in general, it can be very hard to start with your initial substrate and be able to visualize a sequence of reactions that will take it one step at a time from where you start to where you want to end. Some people can do it, and again, some synthesis problems are simpler than others, so for some problems you might be able to. But in general, this is something that is very, very hard, very challenging, and to be honest, it's something that often I can't do. So instead of looking at the initial substrate and trying to find your way forward, I suggest you treat every synthesis problem like a Christopher Nolan movie and start at the end and move back to the beginning. And this strategy, this technique, is something called retrosynthesis. All right, this method that I'm about to use is called retrosynthesis, the retrosynthetic method, and it 9 times out of 10 is how I still solve synthesis problems. And what we do when we do retrosynthesis is we look at the final product and we ask ourselves, okay, we don't ask ourselves, how do we make this from the start? We just ask, what would be one reaction we could do? What is one reaction we could do that would make this product in one step from two things, from any two things, all right? And the arrow that you use when you're doing retrosynthesis is called a retrosynthetic arrow. And you go like this, and you go, okay, how could I make this molecule in one step from any two things? And the first thing that I see is, when I look at this molecule, is I kind of envision it in two pieces. One piece is this alkyne. The second piece is this ring with the OH. And carbons that have alcohols, i.e. this guy right here, that I'm highlighting with a green asterisk, it's alcohol bearing, sorry. Oxygen bearing carbons tend to be good candidates for forming carbon-carbon bonds, all right? And we could make this molecule from a reaction of, I'm actually regretting using green on both sides here. Give me 1 sec. I'm going to change my colors over here. I'm going to color this side blue. All right. So this blue side of the molecule could have come from a ketone, and the green side could have been a terminal alkyne, right, with an H. All right. We could make that end product if we had a reaction or did a reaction with both of these two molecules. The reaction that I'm thinking of is if we added a very strong base like sodium amide to the mix, it would deprotonate our terminal alkyne, and then that anion could attack the carbonyl carbon to make that carbon-carbon bond. So treating it, you can turn a terminal alkyne into a very strong nucleophile by treating it with a strong base, and that nucleophile would attack the carbonyl carbon, making our final product. All right. Now, let's take a look at the alkyne. The next step, after you get one step back, one step removed in your retrosynthetic analysis, you ask, how do you make that alkyne? And we're going to do a retrosynthetic arrow. So where would this come from? All right. Well, again, we know that we can turn a terminal alkyne into a nucleophile through deprotonation, so we can attach various R groups onto the alkyne. So I'm going to, again, kind of divide this molecule into two halves. One half here being the alkyne, and the second half will be this R group. We can make this molecule, this synthetic intermediate, by treating, again, doing the same reaction that we did before. If we treat this alkyne with a strong base like sodium amide, and so this is the, again, the green part of the molecule. For the yellow part of the molecule, so we can use sodium amide to turn the alkyne into a strong nucleophile, but that needs an electrophile to an attack. We need an ethyl R group, but we also need a leaving group. So let's throw, say, a bromide on there and have this be the yellow molecule. All right. And now you'll notice that we have, through our retrosynthetic analysis, discovered our original starting material. And so now we know how to connect this series of reactions together. Step 1 will be here. Actually, step 2 will be here. So this is turns out a 2-step synthesis. I thought it was going to be more complex. Turns out to be fairly straightforward. Once you've found your starting material in your retrosynthetic analysis, to answer the question, you still need to write your synthetic scheme. So let's do that here. But your retrosynthesis will serve as a roadmap to lead you back to the molecule you are after. So here's the answer to that question. Here's our actual synthetic scheme. All right, we are going to start with acetylene. All right, and in our first reaction, we're going to treat our acetylene with sodium amide. And this is important. When we use ethyl bromide, we need to explicitly state that we're using one equivalent. If we use more than one equivalent, the sodium amide will deprotonate the other half of the acetylene and we'll end up adding 2 ethyl R groups. We don't want to do that because we want the second H available for the second part of the reaction. All right, but using one equivalent, we'll put one ethyl group on one side of the acetylene molecule. And then in the second step, we're going to do the same thing, sodium amide. But this time, we're going to use a ketone as our nucleophile. And we want to, so this will be first, we need a second workup step to protonate the alcohol, or sorry, to protonate the alkoxide, turning it into an alcohol. All right, so the final product after the second synthetic step is there. Cool. So that is the answer to that synthetic problem. Sorry, when I first laid eyes on this problem, I thought, oh, this is good. This will be multi-step. This will be challenging. But turns out it was a fairly easy synthesis. But again, that is the power of the retrosynthetic method. It can take something that might seem very difficult or overwhelming and really simplifies it down for you. So let's try to find another problem here. Maybe a little more a problem that's a little more tricky. Let's see. Okay, I'm gonna keep looking at that. That worksheet looked like it didn't have a lot of synthesis problems on it. Let's see. Oh, I know. You know what? Let me do this. So that was a good warm-up problem. Let's maybe do one with, it's got a little more of a bite to it. I'm going to pull up one of my old exam problems from when I taught this class at a different college. But still, OChem doesn't change. Well, it does, but this class doesn't. It's pretty consistent. Okay. Let's see here. Yeah. Let's see, exam 2 maybe. Or maybe it was my third exam. Let's see. Yeah, let's look at the third exam. Also, BT Dubs, if you guys have more questions, totally feel free to lob them my way. I'm searching for... Searching for a good synthesis problem. Let's see. I'm trying to see if these are appropriate or if they're a little bit beyond. That one seems a little... easy. Sorry, some of these, oh, weird. Oh, dang. That's weird. Sorry. I'm sorry. I'm looking for synthesis problems, and sometimes I can get a little kid in a candy store. Well, that's to propose a mechanism. Okay. All right. Okay, sorry for the lag. If that first synthesis problem seemed a little straightforward or disappointingly simple, um, um, oh wait, no, go away. Not you, Irving. There was a pop-up ad as I'm looking for good synthesis problems. Here's a synthesis problem that might be a little next level. All right, a little weird, but I think it'd be a great problem to do because typically organic chemistry professors like to play mind games, right? We like to write something that looks weird to try to freak you out psychologically. But and so here's a problem a synthesis problem that I wrote for a class. This was fall of 2016, first semester OChem, right where you guys are at. This was on an exam that I wrote. So here, let's. So here's the problem. So propose a synthesis using any carbon source with 3 carbons or fewer. All right, let's take a crack at this. So we're starting from 1-phenyl cyclopropanol. And I'm asking you to propose a synthesis for the following molecule. All right, this one's a little weird. Oh, wait, hang on. Okay. Wait, did I draw that right? Hang on. Okay. Excuse me. Okay, so let's figure this situation out. All right. Again, we are going to use the retrosynthetic method. All right. So to do so, I'm going to actually, I'm going to redraw this on the next slide just because I know We're going to run out of room really fast. All right, so let's take our final product, redraw it here. Also, I guess just so I'm not confusing, just so we're all on the same page here. I don't know if all of you are familiar with the abbreviation Me, but this is CH3, right? So Me equals methyl. Just in case you were wondering what that was. Oh wait, I drew the wrong thing over here. Hang on. I'm pretty sure I drew this as the cis. Double cis. Yep, I totally drew this wrong. Let me fix it. All right. This is our product that we're trying to synthesize. Okay. So here's the deal. All right. When I look at this molecule, I ask, okay, how? So you look at your molecule and you go, okay, what functional groups are on here? How can we make this molecule in one step? And the first thing that jumps out to me are these cyclopropanes. I don't know why I'm doing the dash thing. All right, we've got 2 cyclopropanes here. And this cyclopropanes are this annulation reaction, ring-forming reaction, is something that comes to us straight out of our alkene reactivity, right? That's something that we can make from alkenes. So if we can make this final product in one step, if we had 2 transalkenes. All right. Oops. All right. So if we had 2 transalkenes, we could get this final product in one step simply by using two equivalents. All right. This can be done through the Simmons-Smith reaction. So the reagents here that we would add would be CH2 E2 and zinc would do our cyclopropanation reaction. All right. Now, that's how we go from these alkenes to our cyclopropanes. The question now becomes, where do we get trans alkenes from? How can we make trans alkenes in one step? And this can come, you can get trans alkenes through a partial reduction of 2 alkynes. Right, so if we had 2 alkynes here, we could make we could make our transalkenes if we used our partial reduction conditions. And to get the trans partial reduction, this is where you use lithium and ammonia, NH3. That would give you the transalkenes. The cis partial reduction comes from Lindlar's catalyst. So we could go either way, but for this particular problem, we need trans. All right, now here's the question. How do you attach an alkyne to something? Right? How do you get that alkyne on there? Well, this is something we were actually doing in our previous synthesis. You can attach an alkyne to a carbon chain if there's a good leaving group there, right? So if we had, for example, on this position, if we had a bromine, let me just draw in my other alkyne. We could make this product from bromine and acetylene, not acetylene. Sorry, acetylene is two H's on either side. If we treated this with a strong base, like sodium amide. All right. And we could do the same thing with this alkyne, right? If we could make this from the following cyclopropane, and the terminal alkyne, if we treated the terminal, whoops, why am I putting a bromine there? If we treated the terminal alkyne with sodium amide. All right, so now we're almost there. We're almost home, right? The question is, how do we get this product from our initial substrate, which is 1-phenyl cyclopropane? All right, how do we get that product? All right, because what we need is some way to connect this and this. All right, now there's a couple ways. There's one way that I'm thinking of off the top of my head that might be a little step intensive. It might be a little steppy. So I don't know if it's per se the best way to do this. And for some reason I want the best way. Let's think. The first thing that comes to mind is we could use a radical reaction. If you do not have this in your back pocket, you definitely want it. NBS and light is a radical bromination reaction that will put a bromine on your phenyl. All right? So that's one way to that adds functionality. All right, let's do a little more retrosynthesis here. I actually think it'd be a more useful way to go. So you'll notice that at this moment in our retrosynthesis, we have a dibromide. And where do we get dibromides from? Whoa. Dibromination can come from, whoa, dang it, an alkene, right? If you treated an alkene with Br2, you'd get a dibrominated product. I'm going to clear some space down here. All right. Now, how do we make this substrate? Well, we could potentially, let's see. Well, we could do it with an elimination reaction, right? If we did an elimination reaction here, we could get to if we had some leaving group here and we used maybe a strong bulky base like potassium tert butoxide, we could totally get to that alkene. The question is, how would we put this leaving group here? Like we said, I already know that I can brominate. We can put a bromine there, but what we want is a bromine that's pushed one over. And I know a way to do it. I just don't know if you've learned this reaction yet. I don't know if you've learned in your study of Sn1, Sn2, E1, E2, in your study of leaving groups, if you've learned the tosylate leaving group yet. If you haven't, then you can know that this problem would be beyond the scope of what you could be tested on, right? Because it involves reactions you haven't learned. But I'm going to show it to you. If you haven't seen it, you can hang with me and learn something new, maybe. So, tosylate leaving group is represented as OTOS. This comes from, you get a tosylate by reacting an alcohol, so an OH, with a reagent called tosyl chloride. All right. How do we get an alcohol there? Well, we could get an alcohol there from doing a anti-Markovnikov addition of water. Right, so from an alkene, using BH3 and THF, followed by sodium hydroxide and hydrogen peroxide. All right, and this alkene we could get by doing an elimination on a bromide with a strong bulky base like potassium tert butoxide. And now we found our way all the way back to our starting material, because you can get this brominated cyclopropane by using NBS, radical bromination. So this is our retrosynthetic scheme. Now, this will serve as the roadmap to writing the answer to this problem. Let's use it to move in the forward direction. All right, so starting from... Oops. starting from our 1-phenylcyclopropane. Our first step is going to be NBS and light. That will brominate at the benzylic position. All right, second step will be KO-T-butyl, potassium terbutoxide. This will give us our elimination product. Next, we're going to do the anti-Markovnikov addition of water, BH3 and THF. Second step, sodium hydroxide, hydrogen peroxide. And this will give us the anti-Markovnikov addition of water. The next step in our reaction will be a tosylation. Oops. So you can use tosyl chloride and usually a pyridine base. To tosylate our alcohol. Finally, not finally, I don't know why I'm saying finally here. We can eliminate that again with our E2 base. Potassium terbutoxide. To get our alkene. And now we're going to start cooking with gas because we have our alkene. Here, we're going to do a dibromination with Br2. Bromine. And now, actually, rather than doing this in 2 steps, we can actually use 2 equivalents of our 3-carbon alkyne. So I'm going to write 2 equivalents with our strong base, sodium amide. And this will give us a product that looks like it has very, very long legs. Got methyls on the end. All right, now we'll do our partial reduction with lithium and ammonia. That will give us our 2 trans alkenes. And then finally, we do a Simmons-Smith, which is CH2I2 and zinc. And that is the cyclopropanation that brings us to our final product. And now we can breathe a sigh of relief because this is our synthetic target. All right, that was a beefier synthesis. Let's count our steps here. We went through 1, 2, 3, 4, 5, 6, 7, 8. 8 steps in the synthesis. That was a beefy one. Oh wait, 8. What are we talking about? What about the last step? 9. 9 steps. So NELAB. There's two synthesis problems. One, and the funny thing, well, this one probably did look worse, but it honestly probably didn't look that much worse than the first problem we were dished, because it looked very large. We went from a very small molecule to a very large molecule, and the first one ended up being relatively straightforward. The second one, a bit harder, but whether your synthesis problem is hard or easy, you can unravel it using the retrosynthetic method. So there's some cool synthesis. I see we've got several people hanging out right now. Are there any anyone want to throw out any additional questions, either about the problem that I just did, how I did it, or possibly any additional questions? This is honestly the hardest part about holding a virtual office hour or lecture is there's this dead time. See, if we were all sitting in a room, or if you were all sitting in a room, and I was at the board, I could at least look around the room, see, oh, they're writing right now. Maybe I should say something related, or there's some facial feedback. But this is it's at this moment it feels very lonely. There we go. Oh yeah. No, you're welcome, dude. You are welcome. I could totally do more. If you want to see more, I don't know how everyone's feeling. Technically, we've been doing this for like an hour and a half ish. I'm totally down to run the full lab period. We could do this for another hour and a half if you guys want to. If you've got questions or want to see more examples, I'm totally down to hang. Let's see. So most likely we won't have to show mechanisms for each step, right? Okay, great question. So Irving's asking, most likely we won't have to show the mechanisms for each step, like the hydroboration, oxymercuration, demercuration, intermediate steps. Seem long. Okay, so it totally depends upon the problem type. When you're doing a synthesis problem, in a synthesis problem, they're not asking you to write the mechanism for each step. They just want you to write an arrow that shows you the substrate, arrow with reaction conditions, and then product. So no, when you're doing a synthesis problem, you don't need to do the mechanism. For many of these reactions, you want to know the mechanism so that you know what products they produce, but you don't have to explicitly write them out. That is correct. You only write out a mechanism for a problem where they say write the mechanism, draw the mechanism for the following reaction. They'll give you the reactants and products. Then you have to write the step-by-step mechanism. But you won't ever do that for a synthesis problem. How are you guys feeling on mechanism problems? have you guys started? You guys have learned error pushing mechanisms by this moment in the class. So I'd assume that that type of question is fair game. Oh, let's see. Is it cool if we still email you questions tomorrow too? I'm working way through the Alkenes chapter of the homework currently. You totally okay, so you totally can email me questions. However, my ability to get to them may be somewhat limited. I also have an exam going down for my Gen Chem class, and so I'm currently trying to get that ready and out the door. So so I don't know if I'll necessarily be able to get to my emails tomorrow, but you can totally send them in if I can. I totally will, but I can't make any guarantees that I'll have any time before Wednesday. I'm just typing this as a text response so you can see it as well. And I guess this goes, I don't know if I explicitly stated it, but for anybody who's watching who's not in my lab section, you can totally contact me by email or on Canvas. I'm one of the instructors on the lecture Canvas page as well. I'm more than happy to take and answer questions from anyone from any lab section. So so totally don't hesitate if you have questions. Totally feel free to reach out to me. I'll also be holding these kind of open office hour discussion times throughout the semester. And again, everyone's welcome. You don't have to be enrolled in my section to join the conversation. Also, I realize that everybody enrolled in my section theoretically has this time free, and those of you who aren't in my section may not, but you can submit your questions through email. Again, if you send a picture of the problems, I will totally work them in office hours. So even if you can't attend live, you can still see the problems that you're struggling with worked out and hopefully get help that way. I know it's been all the Chem faculty have been scrambling to try to find ways to connect with you and meet your needs, and so I want, if this is helpful, I'd like that to be available to everybody. And anyways, we're, this whole semester has turned into a giant experiment in how well can you pull off remote education. For many of us having zero background in remote education. So it's a little bit trial by fire, a little bit, some people learn to swim because their dads throw them into the deep end of the pool. And that's kind of what life did, what COVID did to us this semester. But my hope is that we're not floundering, and that we can help you swim as well. So more than happy to be there for all the humans in our 420 course, even those who are not in my section. It's also, a different sort of advantage or perspective. I don't write your lecture exams, and so in a sense, it makes me a little more free in my ability to answer questions because I know when, for example, so I held an office hours for my Gen Chem class last Friday. It was our last office hours before their exam hits this week, and when they asked me questions, I had to be a little bit guarded because I know what's on the exam, so I don't want to give it away. Whereas, and I'm sure when you ask Max questions, he's got the same thing going on. He knows what's on the exam, so he doesn't want to explicitly give anything away one way or another. The nice thing about talking to me is I have no idea what's on the test, so I can't give it away, and so you get kind of my candid, unbridled commentary on things, which I'm not saying is better or worse, but it's just something different, you know? So, okay, so we're dropping viewers a little bit. I think I'm basically just talking and rambling, at this moment in time. But I do want to know, what else do you want to talk about? Are there problem types you want to have answered? Are there conceptual things that you're struggling with? Um, what else is out there? So we bumped back. I was gonna say it looks like our feed is dying, but we just bumped back up to 7 concurrent viewers. Though only Irving and Neelab are talking to me right now. And even then, it's been a minute. Oh, let's see. Well, for some mechanisms, why is it that? Okay, so Irving's got a question. He said, for some mechanisms, why is it that we use certain things like acid catalyzed? Why would we use H3O plus compared to oxymercuration, demercuration, if they lead to the same result? That is an excellent question. Excellent question, Irving. So, so you may, so as you know, here. Give me 1 second here. All right, so that is that, Irving. That is an excellent question. So, you all made it through the alkene chapter, right? You learned all about hydration of alkenes, and you learned about what's the word I'm looking for? You learned about Markovnikov addition of water and anti-Markovnikov addition of water, and so you learned that there's actually a couple different ways to do Markovnikov addition of water. For example, if you took the following alkene, I'm just going to put an R group there, and treated this with a strong acid, H3O plus, and water, you would get the Markovnikov addition of water to form a secondary alcohol. You could also, instead of using a strong acid and water, do oxymercuration and demercuration. So you could use mercury 2 acetate. I need a little more room under my arrow, or over my arrow. Mercury 2 acetate, water, and THF. And then second, the demercuration sodium borohydride and sodium hydroxide. All right, and this will give you the secondary alcohol, same product. And so Irving's excellent question is, same product, different conditions. Why? Why would you use one over the other? And the answer is so, as we'll see later this semester and going into next semester as well, there are some functional groups. So some functional groups decompose in the presence of acid. Oh, I'm going to run out of space there. When exposed to acid. So there are some compounds that'll decompose, that'll rearrange, that you will not be able to use the first set of conditions on. So oxymercuration will be your only recourse. That's one reason. Another reason is the first reaction. Let me select together. This reaction involves carbocations. A carbocation intermediate. And that can lead to possible carbocation rearrangements. So another reason why it's good to have oxymercuration is, for example, if you took the following substrate and you did H3O plus and water. All right. So clearly we're trying to hydrate our alkene. The product for this reaction is not a secondary alcohol. All right. It's not a secondary alcohol. The product is actually this tertiary alcohol. All right. And if you're wondering why, we have to look at the mechanism. So the first step of this mechanism is protonation of the alkene, right? So we have our alkene attack. Oh. There we go. All right, so our first step is protonation of the alkene, which will form a carbocation on the secondary carbon. But what happens next is you'll notice that we are dealing with a secondary carbocation here, and we're right next to a tertiary carbon center. right? And so this carbocation will actually rearrange to form a more stable carbocation in its place. All right, so we make a more stable tertiary carbocation here. And when we do, our oxygen on water attacks. We make our new carbon-oxygen bond. Whoa! Or some weird alien symbol. There we go. And then in the final step of this reaction, another water molecule comes around. Oh. And deprotonates to form the alcohol. And that's how we get this weird product, all right? So if you use acid on this substrate, you do not actually form the secondary alcohol that we were expecting. However, that being said, if you do oxymercuration on this substrate, so again, conditions mercury acetate, mercury 2 acetate, water, THF, and then step 2, we have sodium borohydride and sodium hydroxide. Let's see, Photoshop's taking a minute to catch up here. Ooh. Again, it looks like we're receiving alien communication. It's leaking into our video here. We get sodium borohydride and sodium hydroxide. You get the expected secondary alcohol product. So, Irving, this is a very long, roundabout answer to your question, but the reason why you may prefer to use oxymercuration over acid hydrolysis is you may have a molecule that decomposes or is in the presence of an acid. In addition, because oxymercuration does not involve a carbocation intermediate, you can actually avoid carbocation rearrangements and unexpected products as a result. So it tends to be a safer way to go when you want the obvious product. Now, there is a chance that maybe you did want a tertiary alcohol for this substrate. Then you want to do the acid hydrolysis because that will give you the carbocation rearrangement. So there are different ways to do the same things. Oxymercuration tends to be a little more gentle than acid hydrolysis, which usually is a good thing, but again, not always. It gives you an opportunity to stay flexible. That is a very long answer to a relatively straightforward question, but thank you for asking. I hope it was helpful. Alrighty. Are there other questions out there? If you hear noises coming from the other room, shouts of joy or agony, it's because my brothers, who are, how old are they? 28 and 23, are playing Super Smash Brothers with my 9-year-old. So if you're if you're hearing the shouts of joy or agony, that's what's going on in the other room. But we're doing something far more fun. We're doing organic chemistry. Am I right? I think so. You don't have to agree. See, the funny thing is, in this instance, my 9-year-old has a distinct advantage because they're playing on a Nintendo Switch, and my brothers and I cut our teeth on Super Smash Bros. Using the OG GameCube, which had GameCube controllers, which is the best way to play Super Smash Bros. And my 9-year-old is used to the Switch is all he's ever known, so he's used to the Switch controller, which gives him a bit of an edge over his uncles, and I think that's kind of fun. Let's see. Let's see. Nothing new's come through the inbox or email. We allegedly still have 7 people watching. Are there any other questions? Any other things that I can explain, help out with, solve, ramble about? I'm good at that. Throw me a bone and an organic chemistry bone, and I will talk about it till there is nothing left. Anything else? If not, I'll be concluding the stream. Again, I'm totally down to hang out for the full lab period. But if we're out of questions, then I will be calling it a night. And in case you're wondering, this is not me being eager to go and play Super Smash Bros. Once this is concluded, once this is finished, concluded, I'm going back to writing my Gen Chem exam, which is not finished yet. So, all that to say is, if you're wondering, is this me trying to bail on this so I can go do something fun? The answer is no. This is the most fun I get to have today, which is hanging out with all of you guys talking about OChem. And then afterwards, after this is done, I go back to the drudgery of writing Gen Chem tests. So thank you for being the highlight of my day, though. That has been awesome. For me, at least. Probably a little more stressful for you, because I realize there's an exam looming on the horizon. Alrighty. Alrighty. If there are no other questions, then I will be concluding our stream for tonight. Sorry, just taking one more look at the email. Thank you to everyone who came out, who joined in the conversation, or who watched comfortably and silently from the shadows. I'm hope that everyone felt welcome, and I'm glad that all of you were here. Again, this is something that I'm going to be doing regularly, 6:30 till whenevs. Again, regardless of regardless of what lab section you're in, totally feel free to come by and say, hey, I will be, if you were unable to attend live or want to come back and watch this video, but you don't want to have to slog through the mammoth 2 hour, or we're not quite 2 hours, we're an hour and 46 minutes in. I will be in the comments kind of creating an outline. Oh, there's an alarm. An outline with links to different moments in the video, so you'll be able to click like, oh, first synthesis problem. You can click on the time signature. It'll take you right there to that moment in the video. Second synthesis problem, etc. So you can find that outline in the comments, in the description. I'll have those links there to make it easier for you to view. In addition, I will also be posting the slides from this office hour. And normally I'd post them to my lab section under the files, but I'll upload them to the lecture section. That way everybody can access them and download them if you'd find that helpful. Anyhow, thank you all for showing up. It's been awesome hanging. I wish you all best of luck on your exam, and can't wait to hear how it went out the other end. I will catch you all later.